Okay, folks, welcome to the next lecture in Chapter 7. We're going to be looking at the law of signs, and specifically as it has to do with the ambiguous case of triangles. Okay, so the description of the ambiguous case is that if we're given the length of two sides and the angle opposite them, so side-side angle, then it's possible that we have no triangles with that data. One triangle or two triangles may exist. So we have to kind of be very careful when we're given, again, a side-side angle. So two sides and an angle that is not between them, okay? So what happens is the measurements that are given can be such that it causes the sine of b to be greater than 1, which is impossible. And if you look at the diagram, here we have a measure of a that is so small that it will not allow us to kind of close the triangle, okay? If our sine of b is equal to 1, then we have a right triangle, and we would solve it like that. And you would solve both the cases of the one triangle pretty much similarly, whether it's a right triangle or not. And then, of course, if the sine of b is between 0 and 1, then side A would be bigger than side B in this case here, okay? And then finally, we have the case where, again, the sine of, when we figure out the sine of b is between 0 and 1, if that angle, for example, in the case above, is an acute angle, then it's possible that we have a second angle that's in quadrant 2, where sine is still positive, that also may create a triangle. And actually, you can see here we have two ABC triangles in this last case. We have this little end, AB1C, but we also have AB2C, okay? And so again, when we're calculating the sine of the angle using the law of sines, if we get an acute angle measure, something below 90, then it's possible that we could use that as a reference angle, find the angle in quadrant 2, and see if that angle and the other given angle, add up to less than 180. Then it's possible we have a second triangle there. Okay, we're going to look at all these cases in more detail. So this description is just kind of high level and maybe still a bit confusing. But again, when we have side angle, it's possible that we have no triangles, a right triangle, a non-right triangle, a single triangle, and also possible that those measurements could create two triangles. Okay? If that angle A is obtuse that we find, then there's only two possible outcomes. Either we have one triangle or no triangles. And again, when we're talking about angle A, we're just talking about whatever angle we solve for. If that angle is obtuse, then of course we cannot have a second angle A. All right. So how do we apply the law of sines? Okay, for any angle theta of a triangle, we know that of course sine has to be between 0 and 1. If the sine is equal to 1, then we know that the theta is 90 degrees and the triangle is a right triangle. Okay. Notice that the sine of theta equals the sine of 180 degrees minus theta. This is just the idea that if we solve for theta and we get a acute angle, a reference angle, because sine is the y value, it's positive in quadrant 1 and quadrant 2, then we could also possibly have a secondary angle in quadrant 2 that also could build a possible triangle, okay? Supplementary angles have the same sine value. And that's this, to me, it's easier to think of this in terms of reference angle. What would be the reference angle in quadrant 2 if we solve for an angle? This is really important and it's also really kind of easy to remember. The smallest angle is opposite the shortest side. The largest angle is opposite the longest side, okay? So if you have a bigger angle, if angle A is bigger than angle B, then side A has to be bigger than side B, okay? So it's very intuitive. You know, the smallest angle is opposite the smallest side, the largest is opposite the longest side, the middle is opposite the middle side, okay? But that can be very helpful in figuring out which triangles we have. Sorry about that, guys. So let's look at our first case. Solve triangle ABC if B equals 55 degrees 40 minutes, side B equals 8.94, and side A equals 25.1 meters. Okay, so here we can find angle A by using the law of sines, right? So let's plug in all our numbers. And here we get the sine of A is equal to 2.318, etc. So in order to find angle A, we're going to use our calculator and do an arc cosine or inverse sine. We don't even need to do that. I wasn't even thinking. If the sine of A is equal to 2.31, we know that sine, the maximum value of sine is 1, is impossible. So automatically we know that no triangle exists with these measures, okay? That's interesting. If we had tried to do an inverse sine with this 2.31 number, we would have got an error, and that would have alerted us as well, okay? If we saw this, this is what happens when we have angle A being so much larger, or excuse me, side A being so much longer than side B, and we can see that there's no way for this B, that's what this little curve is, if you rotated it around, there's no way for B to reach all the way back down to side C to close the triangle, if you will. Okay. We've already mentioned this. I'm not sure why this slide is here. I should have taken it out. In the ambiguous case, we are given two sides and an angle opposite one of the sides. Side angle. Okay. Let's look at another case. If ABC, or excuse me, solve triangle ABC, if A equals 55.3, side A equals 22.8, and side B equals 24.9. Again, using the law of sines. Notice what we've done here, though. We've used the inverse law of sines. We had the side over the angle, or the trig function, but you can do it either way. And whatever you're solving for, in this case we're solving for B, you want that to be in the numerator, so you can just multiply both sides by the denominator underneath that variable you're looking for. It just makes it easier to solve instead of thinking about reciprocals. Okay, so whatever you're looking for, put that in the numerator with the law of sines. If we were looking for the side B, we would have B over sine of B equals A over the sine of A. But since we're looking for the angle B, we're going to put that in the numerator. Okay, so we set this up, pretty straightforward. Put it in our calculator and we get the sine of B equals 0.89768. So we know that that is a valid possibility. It's between 0 and 1. Using our calculator, we find the angles in quadrant 1 and quadrant 2 that would match that. Okay, in quadrant 1 we get 63.9, which is our reference angle, and then in quadrant 2 we get 116.1, and we find that second angle simply by subtracting the reference angle from 180 degrees. Okay. So now we have to check to see if the larger angle for B is possible, okay? And a way we can do that is simply add A and B together. Angle A is given, add B together, and see if we have any space left, if there's still room for an angle C. So we have to make sure that it's less than 180. When we add A and B together, we get 171.4. So the second angle B of 116 is possible. Doesn't mean it is an actual solution, but it is possible. So what we're going to do now is we're going to solve for two different triangles. A B1C1 using this measure of B, and a B2C2 using this measure of B, and seeing if both of them create actual triangles. Okay, so let's continue on. Solving for our first triangle, remember for solving for triangles we need all angles and all sides, so we still need angle C and side C. So angle C is easy to create because all we have to do is subtract A and B from it, right? Because we have two of the angles and we know that the three add up to 180. So for C we get 60, for angle C we get 60.8, and now we can use the law of sines. A over sine A equals C over sine C, and again here we're looking for the side C, and so we're going to put that in the numerator when we use the law of sines. Okay, we don't use B over the sine of B because B was a calculated value, right? And so we want to use the original value. So we're always going to use A and sine of A because these were given in the original problem and we don't want to have any rounding errors. So we can see that the side of C is 24.2, and we can actually graph that triangle and it looks like this. So there is one possible triangle there. Now let's see if there's a possible triangle with that second measure of B, which was angle B, which was 116.1. So we're going to do the exact same steps that we did up here for this second triangle. We're first going to figure out what angle C2 would be, and then we're going to figure out what side C2 would be. So here we have, again, we do the same thing, 180 degrees minus those 2 degrees given, A and B, and we get 8.6. We then plug that into the law of sines, A over sine A, side C, 2 over sine of C2, and we just have calculated the angle C2, so we can do that as well. We plug in all the numbers and we get 4.15 feet. So all of those measures work out, and there's the triangle. It's quite interesting to see how with those side A, side B, and angle A of 55.3 that were given, we actually have two different triangles that we could create, and they're very, very different, okay? So this is the case where we would have two possible triangles, okay? And hopefully that was clear about how we check the larger angle to see if there's still room left, if you would. Okay? Let's look at another case. Here we have angle A is 43.5, side A is 10.7, and side C is 7.2 inches. All right? So again, we want to find angle C. So we're going to use the law of sines. Again, we put the angular measure, the trig function, on top because we're trying to find out what the angle C equals. And so we get the sine of C equals 0.46. That is between 0 and 1, so that should give us an angle. And we can find that by using the arc sine or inverse sine of this number, and we get the angle C equals 27.6 degrees. Since this angle is acute, there's another possible angle for C, which again is the reference angle we just found, subtracted from 180, which gives us 152.4. However, notice that side C is 7.2 and side A is 10.7. So little c is less than little a, or side C is less than side A, which means that angle C also has to be less than angle A. And in this case, the second angle of C is 152.4. It is not smaller than 43.5. So this isn't possible. Another way you could do that is simply to take this angle, add it to A, and you immediately see that we have, when we add angle A and C, we have an angular measure of greater than 180. So there's no way that those two angles could be built together inside of a triangle. So we know that there is not a second possible angle for C, even though there was a possibility from a trig perspective. There's not another possibility from building a triangle. So this triangle only has at most one triangle. Okay, so let's solve for that one triangle. We need to find the other angle, which is B. That's the simple part of subtracting the two other angles, A and C. And then we have to find side the length of side B. And of course, we use the law of sines with the side, our lowercase b in the numerator, and calculate it. And I'm not going to go through those calculations. We've done enough of them already. You should be able to do them. You can slow down and pause this and make sure you've got the right answers. But you can see the triangle here as well. Okay? What happens if we have an obtuse angle? Notice, without using the law of sines, explain why A equals 104, little a equals 26.8, and B equals 31.3 cannot be valid for a triangle ABC. So hit pause and see if you can figure out why that would be the case with this specific measurements, okay? We certainly have enough bandwidth. We have 104 degrees, so there's plenty of room left in the triangle. But notice that A is 26.8 and B is 31.3. So this says that angle B would actually have to be greater than angle A because side B is bigger. Remember, the largest side is opposite the largest angle. Since B is larger, then we expect that angle B would be larger than 104. And a triangle cannot have two obtuse angles. So B would have to be greater than 104, say 105, and that would give us degree measure of 200 plus. And so that's not possible. Because A is the obtuse angle, it must be the largest. Thus side A, lowercase a, must be the longest side of the triangle. And we can see that we are given that B is greater than A, so this is not possible. Okay, this is a rather short lecture for 7.2, and hopefully this was pretty well explained, and you can do some of the problems to gain mastery in this ambiguous case.